Welcome back to Chem 4300. In this video, we're going to continue Chapter 8 on classical wave motion. And now we're going to turn our attention to waves where the symmetry of the wave is such that the Cartesian coordinate system is not really the most appropriate coordinate system, but in fact, actually, like in this case here, we will see that coordinate systems like the polar coordinate system in 2D or in 3D, maybe spherical coordinate system would be more appropriate in those cases. So what I'm going to do is look at the conversion from a Cartesian to spherical basis, and the polar coordinate conversion will be just a special case of that. Now, generally speaking, you know that when we have a Cartesian coordinate system, x, y, and z, that we have unit vectors associated with x, with y, and with z. Now, in a spherical basis, we're going to have three coordinates. We're going to have r, theta, and phi, and we have r, theta, and phi, and we will also have unit vectors associated with those coordinates. So we'll have er, e theta, and e phi. Now, when we transform the gradient operator from Cartesian form, so here it is in Cartesian form, into spherical form, this is a little challenging problem, but this is something you could do in a homework set, but I don't expect you to follow this here. But this is the result that you get. So this is the Cartesian operator transformed into spherical coordinates, the gradient operator. So here you see there's er, unit vector, e theta, unit vector, and e phi, unit vector times these partial derivatives here. Now, the polar coordinate case is just the special case where theta is equal to 90 degrees. So sine of 90 degrees is just 1, so that term just becomes 1. And of course, if theta is constant, then that term would just go away. And that's what you would have for the polar case, just that term and this term with theta equals to 90 degrees. Now, the Laplacian operator, which we learn is given by that expression in Cartesian coordinate system. If you transform this into spherical coordinates, it looks like this. Now, that's pretty kind of scary if you're only seeing it for the first time, but we're going to be using this expression over and over again throughout the semester, particularly when we get into the quantum mechanics. And so here it is again, and for the polar version of this, you just simply set theta equal 90 degrees, which means this term just goes to 1 here, and this term just goes away, and you'll have the polar version. Okay, so that's the conversion to spherical, and then which has a subset with theta equals 90 of polar. Now let's look at a problem in 2D. And so we're going to focus on this problem where polar coordinates is more appropriate. So you imagine a drum, and you hit the drum with a drumstick, and you set some wave motion into play. What we want to know is what are the normal modes on this drum head, and how can we describe any wave, for example, when I hit it with the drumstick, in terms of some linear combination of those normal modes. So what we're going to do is focus on this problem, which has the boundary condition that the wave function has to go to 0 at the edges. So we have a circular membrane with a radius a, which is attached to some kind of fixed supports where it can't vibrate at the edges. And so now we know it has to go to 0. So in polar coordinates, that constraint is very simply written. It says that the wave function at r is equal to a, at the radius here, where the rim is equal to 0. So for all values of phi and all values of time, when r is equal to a, the wave function must go to 0. That's our constraint. Now, when we go back to the wave equation in terms of polar coordinates, and you can check this by going back to the previous slide, this is what we have. So what we're going to do is we're going to propose a wave function on this circular membrane that has this form. So we're going to use the separation of variables trick, and we'll plug it in and see if it works, but this is going to work, I promise you. And so we plug this into this wave function and do a little rearranging, just like we've done previously, and I put it in this form here. So what you see is we have everything that depends on the spatial part on the left and everything that depends on time over here on the right. Now, the only way for these two sides of the equation to be equal to each other is that they're equal to a constant, which we call the separation constant, which I'm setting equal to minus omega squared for reasons that we've already seen before. So we have taken our partial differential equation and we've pulled out an ordinary differential equation for the time-dependent part. And we've already worked out solutions for this, so we don't need to bother with that anymore. We know what happens here in that solution. So now let's focus on the spatial part. So this is what's left over. We have still a partial differential equation with respect to r and phi, and it's equal to this separation constant that we got up here for the time part. So I'm going to rearrange this again, and so you can check this out here, but you can rearrange this and you can get it so you have everything that depends on r on the left and everything that depends on phi over here. And again, for these two guys to be equal to each other, for all values, they must be equal to a constant, which we're going to assign to a separation constant of m squared. Again, for reasons that will be apparent in the coming slide here. So this is our separation, and this gives us now an ordinary differential equation for phi and an ordinary differential equation for r. So let's focus on the angular part here. Here's the ordinary differential equation for phi, and solutions for this equation have this form, and that's fairly straightforward. You can check that yourself by substituting that in there and verifying that that will work. One of the requirements that we have in polar coordinates is that this coordinate phi, which goes from 0 around to 2 pi, when it comes back, if it goes 0, 360 degrees, when it comes back to where it started, the wave function has to have exactly the same value. So we can't have a discontinuity where you get to 360 degrees and 0 degrees. They have to have the same value, so we can't have a gap between them. So we require that whatever the wave function does, it has to come back in that 360-degree turn to exactly the same value when it hits 360 and 0 have to have the same number. So we're going to represent that by saying phi plus 2 pi has to be equal to the value at phi. So if we take this solution and we plug in phi plus 2 pi on the left and set it equal to the solution at phi, just phi, so we add pi on this side, making sure it equals this side. The only way we can make this happen is that we require that e to the plus or minus I m2 pi be equal to 1. This constraint, which follows from that constraint, means that we can only have integer values of m. M can only be values of 0, plus or minus 1, plus or minus 2, and so on. All right? Okay, so that's what we find for the solution for the angular part. Let's move on to the radial part. The ordinary differential equation for the radial part looks like this. And this is a pretty challenging equation to try to solve. And what we'll see is that we can at least try to understand what's going on here in a limit of, we have really large r, because I'm not going to expect you to be able to solve this equation on your own here. We're just going to look up this solution. But before we do that, I just want to show you a limiting case here, which is that when you're far from the origin, so imagine this problem here, and I'm very, very far from the origin of the polar coordinate system. So that's the origin there, and we get very far away. Then that's the case where r is getting big and r squared is getting big, so 1 over r is small and 1 over r squared is even smaller. So if we get very far away, we can neglect that term and we can neglect that term, and that says that the ordinary differential equation describing this wave in the limit that you're very far from the origin will look like this. And that's a very simple 1D wave equation, and this looks like simply, the solutions to this are just simply plane waves, or in this case line waves that are just radiating out. Which sort of makes sense, right? You know that if you were very far from this origin and you were looking at the waves, if you were far enough away, it would just look like plane waves just coming at you. And you probably wouldn't even be able to see this. You were so far away, and you would see these plane waves coming at you. But they were generated by this source here, which is emanating out in this polar symmetry there. Okay, so now what we want to do is focus on what the actual solution of this is, but we now have an understanding of the limiting case of what this should look like. So this is the wave equation, and so what I'm going to do is do a little rearranging of the coordinates here to put it in a form where we can obtain a solution from some previously known solution. So what I'm going to do first is I'm going to define a new coordinate, u, which is equal to k times r, where k is our wave number, so that's omega over vp, and taking the derivative of that gives us du is equal to k dr. Okay, that's fairly straightforward definition. It also means that whatever our function is, r dr has to be equal to ru du, so that means that whatever that interval is of the function, they have to be equal to if we set this side of the equation equal to that side of the equation. And so that means we end up having this using up here, and we get this expression. And so when you put this all into here, you end up with this ordinary differential equation. Now, I went kind of quickly through that. You can check this on your own if you'd like, but if you don't have time, don't worry about that. This is what you get if you make this substitution. And when you get to this point here, you may be wondering, well, what was the advantage of going from here to here? Well, this equation right here is actually something that might be recognized by mathematicians as the Bessel differential equation. So this is well known in mathematics as Bessel's equation, and the solutions to this have been worked out, and they're what are called Bessel functions. So these functions, which are known, actually there are two types of solutions. One is called Bessel functions of the first kind and Bessel functions of the second kind. It turns out for this membrane problem that we'll only need to use these Bessel functions of the first kind. We won't need the ones of the second kind. But these solutions are all worked out. So all we have to do now is just look at the solutions, get an understanding of how they work, and then we can move on into solving our wave problem. So we're going to look at this problem, and we're only going to need to use the Bessel functions of the first kind. So here's what they look like. So this is J0, this is J1, this is J2, and this is J3, and they continue on. So they look kind of like a sinusoid, but they actually decay with 1 over the square root of u, where u is the coordinate here that I'm plotting these against. And the other thing that we see is that there are roots here. So this is the roots where they pass to 0. So just like a sinusoid, like a sine, where we see that there are roots at integer multiples for sine at integer multiples of pi, there are roots here, but they're not showing up at obvious values like they are in the sine case. So these roots are indicated with this notation of u sub m with the superscript n parentheses. So this is the root for J0, the first root for J0. This is the second root for J0. This is the third root for J0, and so on. This is the first root for J1. This is the second root for J1, the third root for J1, and so on. And that's how we'll describe the roots for these Bessel functions. The other thing that's important to note, we're going to need negative values of m2 in our solutions. So there is an identity that says that j with the negative m is equal to minus 1 to the m power times j with the positive m. So if you change the sign of m, you just need to use this relationship here. So for m equals 0, then it's exactly the same, but there's only one solution. But for m equals 1 and minus 1, then you see that minus 1 to the 1 power means that this is going to stay as minus 1, multiplying that guy. So this whole function, j1, is just going to flip upside down, and that's going to be j minus 1. Whereas j2, this is going to be minus 1 to the second power. That's going to make this just 1. So j2 and j minus 2 look exactly the same. But j3, minus 1 to the third power, makes this minus 1. So j3 is going to flip upside down when you go to j minus 3. All right. Now, here's the key point. In our drum, we know that the wave function has to go to 0 at the rim, at the endpoint, when r is equal to a. And so we know that for that to happen, the end of the drum can't be anywhere on these Bessel functions. It has to be one of these roots. So the end of the drum could appear here, 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 and so on, or depending on which normal mode we're looking at. So we require that the end of the drum, where r is equal to a, the wave function has to go 0. So that means that we require that whatever this value of u is, that u has to be equal to one of these roots. So we know that u is equal to k times a. So that means the Bessel function evaluated at k times a has to be equal to k times a is equal to one of those roots. And since those roots are indexed by m, depending on which Bessel function we're looking at, and n, depending on which root that we're looking at in a given m, then the k value can only adopt values associated with the particular value of m and the particular root of that value of m. So this is our constraint. So k can only have values that are indexed by m and n, where this is the root of the nth root of the mth Bessel function. It's hard to say. So with this constraint then, the frequency, which we know is related to the wave number, is Vp times the wave number, the frequency also becomes constrained and now is indexed by m and n, and that's going to be given by this expression here. All right, so we've actually solved the problem. We didn't fully solve it because we just looked up the solution for Bessel's differential equation, but that's okay. And we know the solutions and we can use them. So what we found, this is from the previous slide, we have all those solutions for the Bessel function shapes, and these are where all the roots are tabulated here. So here's the spacing that you have. What you find is the spacing. So these are the different n's. These are the roots going this way. These are the m's going this way. So these are the roots of the m equals 0, and they're not equally spaced. So unlike the sine case, where again where they're all integer multiples of n times pi, right? So if they're all multiples of pi, these are not spaced equally, but they do become relatively equally spaced as you get to larger values of u. So finally then, we come to what the normal modes look like for a circular membrane. And so we remember that our angular part we wrote it in complex form, but if you wrote it in real form, then you would have a cosine and a sine term in that expansion. So now we have this part here, which is the cosine part for the angular part, and it's multiplied times the Bessel function and then the time-dependent part that we had solved earlier in the class. And then we have a sine part here, and there's some relative contribution of those guys. And this is the mode that's indexed by m and n. So each m and n mode has a cosine and a sine part to it, a mode to it. And so each of these modes then has nodes. And so for a mode with a value of n, they're going to be n minus 1 radial nodes. So here's a plot of what the sort of a plot of what the wave functions look like, ignoring sort of the variations in the amplitude. So we're just looking at the sign. So when it's white, it's a positive. When it's green, it's negative. And so we see where the wave function changes sign. Where it changes sign, that's what's called a node. And so we see that there are n minus 1 radial nodes. So for n equals 1, n minus 1 is 0, there are no radial nodes. For n equals 2, there's 1 radial node, and that's right here. For n equals 3, there's 2 radial nodes here and here. And then in terms of angular nodes, there are m angular nodes. So for m equals 0, there's no angular nodes. M equals 1, there's 1 angular node right here. M equals 2, there's 2 angular nodes here and here. M equals 3 has 3, 2, 3 angular nodes, and so on. And so then when you go down here, you see the mix of radial and angular nodes. And that's all predicted by the value of m and the value of n. And this is the case for just the cosine. So if you wanted the sine case, then you simply would just take these shapes and just rotate them 90 degrees, and they would look exactly the same for this set of normal modes. So finally then, we come to our result that any wave function on this membrane, so if I took a drumstick and I beat the drum and I created a wave on that drum head, then it can be decomposed into these normal modes and described by this linear combination here. Okay, so that's the end of this little section here. In the next video, we'll look at a simulation of these membrane waves that sort of makes it a lot easier to visualize how these patterns actually look and how they're decomposed into these normal modes.